In this video, you will learn the relationship between the roots and coefficients of a quadratic equation, as well as how to write a quadratic equation or function using information about the roots or the graph. Now, as we learn the relationship between the roots and the coefficients, we first must understand the solving process of a quadratic equation. All right, so for example, if we had 2x squared plus 4x minus 30 equals 0, and you were told to solve this. Now, assuming we know how to solve, what we can do is we can factor out the 2. Each term has a 2 in common. When you pull the 2 out, you're left with x squared plus 2x minus 15 equals 0. Now here in the parentheses, this can factor further. All right, so when you factor this, you would have the 2 in the front, then you have 2 parentheses, and then equaling 0. So we'd have x and x to get x squared, and then we need two numbers that multiply to get negative 15 and would add to get 2. Well, if we do a positive 5 and negative 3, that would multiply to get negative 15, and that would add to get a positive 2. So we see that typed up right here. All right, now to solve this the rest of the way, what we need to do is we need to set each part equal to 0. Obviously the 2 cannot equal 0, but this x minus 3 could equal 0, or x plus 5 could equal 0. And that's by using the zero product property. All right, now we solve each of those equations that we just created, and we have x equaling 3, or x equals negative 5. So our solution, or in other words, our roots, would be 3 and negative 5. Now our objective in this lesson is to go the other way. So if you're given these roots right here, our objective is to go back this other way to get one of these equations up here. All right, so to do this, okay, let's work backwards, and let's suppose the roots are 3 and negative 5. So we're trying to work backwards. And we're trying to use the relationships that we know to determine this equation. All right, so if the roots are 3 and negative 5, what we know is that this, we need like x minus 3 equaling 0, because when you solve that, right, then you have x equals 3, right? If you have x minus 3 equals 0, x would equal 3. That would be one of the roots. So x minus 3 would be in one parentheses, and the other would be x plus 5, right? Because if you do x plus 5 equals 0, that would give you the root of negative 5. All right, so basically take the opposite signs. So negative 3 instead of positive. Instead of negative 5, we put a positive 5. All right, so we know the equation is going to look something like that. And then from here, okay, we can distribute. We can FOIL, right? We do first, outer, inner, and last. That would give us x squared plus 5x. And then we have negative 3x, and then minus 15 equals 0. And these can combine. We get x squared plus 2x minus 15 equals 0. So here we have created an equation that has those roots. And notice that's exactly what we had right here. Right? That was this exact same part. Now the only thing to keep in mind is that this equation would work. All right. This would be an equation that has this information to be true. But it could also be any multiple of that. So we can take that and multiply by any number. We'll call that a. All right, so any number, in this example that we started with, it was a 2. Okay, it could be a 2 in the front, could be 3, 4, 5, could be negative 1, could be fractions in the front. So it could be any number, any multiple of this equation that we created. All right, so we don't have the same exact equation we started with over here, but we have an equation that has this same information. Okay, that has the same roots. All right, so let's try to generalize what we have created here. So in general, okay, if R1, we'll call that R1, that's roots 1, and R2 would be root 2. If those are your roots of a quadratic equation, then we know that we can set this up as x minus R1 times x minus R2 equals 0. That's what we did right here, right? We had R1, this was root 1, this was root 2. All right, we take the opposite. That's why the minus sign is here, down here. So we take the opposite of each of those roots. So we have x minus 3. We had x plus 5 because that was the opposite of negative 5. All right, so that's how you set up the equation. That's in general. All right, then when you FOIL, okay, if you FOIL this, okay, we'd have x times x to get x squared. You'd have x times negative r2. So we have negative r2 times x. Then inner, negative r1 times x. Then outer, we have negative times negative is a positive. r1 times r2 would be r1 times r2. And then this is kind of weird because it's really not numbers anymore, but these can combine. All right, because those are like terms. They both have an x right here. So when you combine like terms, remember you add the coefficients. So r1 and r2 are just some number, right? So we can add the negative r1. So we have negative and then r1 plus r2 times x. So we combine those coefficients. So we have a negative, it's going to be a negative sign out front, r1 plus r2 times x, and then plus r1, r2. All right, so the point of that was to kind of figure out, in general, what is the relationship. So here's kind of a shortcut, all right? So if you're given two roots, okay, this middle coefficient would be a negative, and then the sum of the roots, r1 plus r2. All right, and then over here, this constant term would be a multiplication, a product of the two roots. All right, so the example we just went through, r1 plus r2 would have been 3 plus negative 5, which would have given us negative 2, right? That's the sum. So it's a negative 2, a minus a negative 2, which makes it a plus 2, which is what we had right here, right? So that's how we got the 2 there. That's a shortcut. Just take a negative and then add the sums together. And then here, for the constant, we took r1 times r2. So if we took 3 times negative 5, that gave us negative 15. And that is what we had for the last term. All right, so down here, this is, in general, a shortcut to get the equation. Instead of going through all these steps, step 1, step 2, all that, okay, we can just jump right to this instead. All right, so here is kind of the same thing. We just wrote it out here as a theorem, okay? So the theorem says, as we kind of already stated, that a quadratic equation with roots r1 and r2 would be expressed in this manner. That's what we just went through in the last slide. Or keep in mind, we could also multiply by any constant in the front. All right, that would also be the same thing. So we can have a times all of that as well. So in other words, we can have a times x squared minus the sum of the roots, right, r1 plus r2, plus the product of the roots, r1 times r2. And that's set equal to 0. All right, so we've gone through the theory behind this. So we worked through why it's true. Now we're going to work with some examples of using that to create an equation. So example 1, we're trying to find a quadratic equation with roots 8 and negative 3. All right, so as we stated, we can use this information, use this theorem, and just basically plug in numbers. All right, so the sum, if we add the roots together, we have 8 plus negative 3, which gives us 5. And the product would be 8 times negative 3, which would equal negative 24. So bottom line, we would just put that right in here. So the minus, opposite of 5, the sum, r1 plus r2, put the minus 5x, r1 times r2, would be plus a negative 24. And we can just write that as minus 24 equals 0. All right, so this is our equation. This is it. So this is an equation that has those roots. Now remember, it could be any multiple of this as well. So we could have a 2 in the front. So you put this in parentheses. You could have some constant in the front. It could be a 2, 3, 4, whatever. But this is one equation which has those roots of 8 and negative 3. Let's take a look at a more advanced problem. Example 2, we are given the roots to be 4 minus 3i over 2 and 4 plus 3i over 2. All right, so this one is more tricky because we have fractions as well as we have imaginary numbers. The I is imaginary. All right, so we have the theorem written here, and it's color coordinated to kind of help you visualize more clearly what's happening. All right, so here, this part when it says R1 plus R2, that means we're adding these roots together. So we take the 4 minus 3i over 2 and add that with 4 plus 3i over 2. Okay, when you add, you add the numerators and keep the denominator the same. So the denominator stays as 2, and you add the numerators. Okay, so you have 4 minus 3i plus 4 plus 3i. I'll write it out in case you're struggling to see this. All right, so notice that the minus 3i and the plus 3i would cancel out. What you're left with is 4 plus 4, which is 8 over the 2, and 8 over 2 would be 4. So R1 plus R2 would be 4. Okay, so that's going to be the number that's going to go right in here, R1 plus R2. Okay, now we need R1 times R2. So now we need to multiply the roots together. Okay, when you multiply the roots, okay, the denominator, you would do 2 times 2 to get 4. So be careful you're actually multiplying and not just keeping it the same. And then the numerator, you have 4 minus 3i times 4 plus 3i. Now you could FOIL everything out, and that would work. But realize there's a shortcut because one is minus and one is plus. Okay, these are conjugates of each other. We've learned previously that conjugates will have the middle term cancel out. So the shortcut would be just do the first, get 16, and then do the last. That's the shortcut. You have negative 3i times 3i. That give you negative 9i squared. If you FOIL out completely, you get 16. Do the inner. Sorry, that's outer. That's first. 4 times 3i would be 12i. That's the outer. Inner would be negative 3i times 4. That's a negative 12i. And then the last, negative 3i times the 3i is negative 9i squared. So just notice these would cancel, and you would indeed still have 16 minus 9i squared. All right, now from here, remember with imaginary numbers, I is the square root of negative 1. I squared is the square root of negative 1 squared. When you square the square root, that cancels. You're left with negative 1. So what we have is 16 minus 9, and then times, that's negative 1. All right, so we have 16, that'd be plus 9, which gives us 25 over 4. All right, so R1 times R2 would be 25 over 4. So the 25 over 4 is what's going to go right here for R1 times R2. So you plug a 4 in for R1 plus R2, you plug a 25 over 4 in for R1 times R2, and we now have this equation. Now it's best to write our equation without fractions. So one last thing we could do is multiply everything by the least common denominator to get rid of the 4 in the denominator. So if you multiply everything by 4, which would be your least common denominator, you would get 4x squared minus 16x plus 25 equals 0. All right, so this here would be our equation written in the correct form. Next, we have another theorem. So this theorem we're going to present to you, and then we will prove that it's true here in a moment. So the theorem says that if R1 and R2 are the roots of a quadratic equation, and the quadratic equation is ax squared plus bx plus c equals 0, then the sum of the roots would equal negative b over a, and the product of the roots would equal c over a. So we're going to prove this to be true, and then we'll explain how we can use this. All right, so we've already stated that this is a true statement, right? We have some constant times x squared minus the sum of the roots times x plus the product of the roots equals 0. Okay, we've just used it in the last 2 examples. We've proven it. All right, so we know this to be true. Now, working with this part, the quadratic equation right here. Okay, if you're given that quadratic equation in general form, okay, ax squared plus bx plus c equals 0. What I can do is I can factor the a out. Okay, factor the a out. And when I do that, in parentheses, I'm left with something. So when I factor something out, what I'm doing is I'm dividing everything by that factor. So I divide ax squared by a to get just x squared. I take the bx divided by a to get b over a times x. And then I divide the c by a to get c over a. All right, so that's how we factor. All right, so when you do that, we now have this new expression. All right, so I try to color coordinate it for you to help you visualize what's happening. So if you compare these two things, compare these two expressions. Okay, notice they're both in the same format, right? We have an a in the front. We have an x squared term here, first in parentheses. And then here, next we have, in green, something with the x term. Here we also have something with the x term. All right, so that's the same. Here we have a constant. Over here we have a constant. These are two numbers being divided, and set equal to 0. So everything is identical. So if you compare these, okay, we know that this part in green must equal this part in green. It's going to be the same number with x, the same coefficient. So we know that those would be equal. Okay, so if those are equal, I can divide both sides by the negative to move this to the right side. And when you do that, you have r1, positive r1 plus r2 equals a negative b over a. So we just move the negative to the other side by dividing both sides by a negative. All right, so this is a relationship we have with those two coefficients. And then look here in yellow, we know that r1 times r2 would equal c over a. So this is a relationship between the roots and the coefficients or the numbers in a quadratic equation. And what this can be used for is it can be used as a way to check the solutions of a quadratic equation. So for example, let's say that we were to find the roots of the equation 3x squared plus 10x plus 2, it should be set equal to 0, so equal to 0. Find the roots of that equation. And we're to check our answer by using the theorem about the sum and product of the roots. All right, so if you have this equation and you're trying to find the roots, different ways we can do that, but the simplest way in this particular case would be to use the quadratic formula. So remember, the quadratic formula says x equals the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. All right, and in this case, we have a would equal 3. That's the coefficient with the x squared term. B would be 10, the coefficient with the x term. And c would be 2, which is the constant term. So what I can do is I can now plug in these numbers into the quadratic equation. So when you plug in the numbers, we would have this. Okay? And then from here, we can simplify. So we have 10 squared is 100. So we have 100, and then we have negative 4 times 3 times 2. That's going to be negative 24, which would equal 76 inside of the radical. And then you have 2 times 3 in the bottom. That gives you 6. All right, and then 76, the square root of 76 could actually simplify further. We could pull out stuff, because 76 is a product of 2 times 38. And then 38 is 2 times 19. So what we have is 2 2's and a 19 inside of the radical. And so what I can do is I can pull out 1, 2, because I have one group of 2's. I'm left with a 19 on the inside. All right, so that square root of 76 can be simplified to be 2 times the square root of 19. And now this entire equation, we can simplify one step further, because we can divide every part by 2. This would be negative 5, this would be 1, this would be 3. So what we have is negative 5 plus or minus the square root of 19 all over 3. All right, so this would be our solution. And notice the plus or minus means we have two different answers, right? Two different roots. So the first root would be negative 5 plus the square root of 19 over 3. And the second one would be negative 5 minus the square root of 19 over 3. So that would be our two roots. So we have our solution, and now we can check our answer by using the theorem about the sum and the product of the roots. All right, so we said if we were to add the roots, okay, this should equal negative b over a. So if we did it correctly, it should equal, remember, a is 3, b is 10, c is 2. So r1 plus r2, we're hoping, should equal negative b over a. And then the product of those roots should equal c over a. All right, so let's try it out. So if you add these together, okay, notice when you add the numerators, okay, you have negative 5 plus negative 5, which gives you negative 10. And the square root of 19 plus a negative square root of 19 would cancel out. So you're left with negative 10 over 3. So negative 10 over 3. Does that equal negative b over a? Well, negative b would be negative 10 over a would be 3. So yeah, that is the same thing as negative b over a. So that concludes that that part is correct. Okay, now we need to check r1 times r2. So if you do r1 times r2, you multiply the roots together. Your denominator would be 3 times 3, which is 9. Your numerator, notice we have conjugates, so again we can use the shortcut. Conjugate meaning one is plus, one's minus, everything else is the same. So the shortcut would be doing the first, negative 5 times negative 5, to get 25, times the last, square root of 19 times a negative square root of 19. Square root times a square root will cancel the square roots out. You're left with just a 19. So you have 25 minus 19, which is equal to 6 over 9, which is 2 over 3. Is that equal to c over a? Well, c was 2, a was 3. So 2 over 3. Yeah, that's the same thing. So what we've done is we've verified that our solutions are correct. Okay, because the sum of the roots equals negative b over a, and the product of the roots equals c over a. So this is the correct solutions that we have. Now to finish off, we are going to work with information given about a graph. And what we're trying to do is we're trying to find a quadratic function that fits the description given. So here, we're trying to write a quadratic function such that the maximum value of f is 6, and the graph of f has x-intercepts of 5 and 9. So as we're thinking through this, first off, remember that x-intercepts, this is another word for the roots. Okay, that is the roots. And for the roots, okay, x-intercepts, that's where it crosses your x-axis, right? So it's crossing on the x-axis. And anywhere on the x-axis, no matter where it crosses, notice y would always equal 0. Like if it crosses here, it's not up or down at all, y would equal 0. If it crosses here, y would be 0. All right, so for the x-intercepts, y would equal 0. And remember, with function notation, f of x is the same thing as y. So f of x, or y, same thing, would equal 0. Also remember, we've already discussed this, that a times all of this would equal 0. All right, we've dealt with that several times already in this lesson. All right, so they're both equal to 0, so what we're doing is we're going to set f of x equal to this. So f of x equals that. That's going to be our initial setup. So we need to fill in all the different parts of this function. Well, r1 plus r2, that is the addition of these roots. Okay, these are the roots or intercepts, same thing. So if we add 5 plus 9, that gives 14. So we have a minus 14x, right? The minus is in the front, plus r1 times r2. We do 5 times 9 to get 45. So what we have is f of x equals a times parentheses x squared minus 14x plus 45. All right, so we're coming along, but the last thing we need is to figure out what is a equal to. What is this constant in the front? Well, thinking through here, we've already used the x-intercepts of 5 and 9. We've already used that information. The only thing we've not used yet is the fact the maximum value is 6. So that is what we need to use to figure out what is a. So we're going to use maximum value to find a. Okay, so at the maximum value, okay, if you think through how this would look in a graph, okay, if it's up at 6, 1, 2, 3, 4, 5, 6, okay, that means the maximum point would be up here, and it's going to be something like that. It's going to be facing down, right? Well, at this point, at this highest value, that is our y value, right? So we know that y would equal 6 at that point. So we know that y is 6. The question is, what is our x value? All right, so y or f of x equals 6. What is x going to equal? All right, well, if we know that the intercepts are 5 and 9, and actually the way this is drawn should have been on the other side, but regardless, this picture can still help us visualize what's happening. Wherever the intercepts are, okay, this middle point, this vertex, okay, this highest or lowest point is going to be dead in the center. All right, so if we know these 2 points, and this in this example is 5 and 9, we need the point right in the middle of those 2. All right, so what point is in the middle of 5 and 9? Well, we simply find the average. So we average 5 and 9 by adding and dividing by 2. That gives you 14 over 2, which would equal 7. So that point would be 7, 6. And again, the way I drew this picture, it should have been on the other side, but the logic is still there. Okay, the halfway point is going to give us that x value of the vertex. And actually here I drew it up more accurately. So this point up here, we said was at 6, that's our y value. Down here our x-intercepts are 5 and 9. All right, and this point right here in the middle, that vertex will be right in the middle. So we average 5 and 9, so add and divide by 2, and that gives us 7. So this vertex would be at the point 7, 6. All right, so we're still not done yet because our goal was to find a, right? All right, so we know that we have this so far. F of x equals a times x squared minus 14x plus 45. We know the vertex is at the point 7, 6. So what we can do is we can use the vertex, use that point that we know, to find a. So to do that, we plug the vertex into the function. All right, so this here, this is my y value. That's going to be 6. Right here, this is my x value. That's going to be 7. So we have 7 squared minus 14 times 7 plus 45. All right, well, 7 squared is 49. 14 times 7 is 98. And now we do 49 minus 98 plus 45. And when you do that, 49 plus 45 would be 94. 94 minus 98 would be negative 4. So we have 6 equals negative 4 times a. Divide both sides by negative 4. You have a equals 6 over negative 4, which would be negative 3 over 2. So a would be negative 3 over 2, and that's what we plug in right up here. So right here in for a, this is negative 3 over 2. So when you plug that in, we now have f of x equals negative 3 over 2 times parentheses x squared minus 14x plus 45. So this would be our function. And if you wanted to, you could distribute. That would be fine as well. Just depends on how you want to write your final answer. And that concludes our lesson for today. We will see you next time.